The fundamental theorem of calculus asserts that the value of a definite integral can be obtained by calculating the indefinite integral of the function. This is indeed the fundamental theorem of calculus, gentlemen, and it is an essential concept in the field of mathematics. It provides a fundamental connection between differentiation and integration, enabling us to solve a wide range of problems in calculus. Why is this important? Didn't we discuss this? Why emphasize? Even if we call the curve we have fx, if we can calculate the integral of the area surrounded by that function, we can calculate the area. If we can perform the inverse operation of the derivative of a certain function, we can calculate the area surrounded by that function. These two are important because they are connected, right? The proof of the fundamental theorem of calculus is divided into two main parts, gentlemen. You should begin with part 1, so I will attempt to explain it as simply as possible. You do not need to summarize or anything, just listen and concentrate. It may be challenging, but I believe you all can comprehend. Listen attentively. There is a minus fx here, and I will write it as a to x, which is widely known as s. From point A to point x, take a look at the large area, which we'll call S. Pay attention here, as I'm going to move x and make changes to it. Consider that x has increased in value. Hey guys, x is currently located here, so let's say x has moved to this new position. Take into consideration the change in x, the symbol we use to represent a change. Hey guys, what is this thing that we're looking at? This is what they call a delta x, you know? So this is how much x has changed. How much has it changed? Hey everyone, so the quantity that has undergone a change is commonly known as delta x. Has the value of x experienced a change of this magnitude, everyone? And then, did anything change? Did the area change? Hey guys, was this thing always here? This thing, there used to be an area surrounded like this. And by the way, a is a constant and x is a variable. I changed x here. So, the area underwent a change. The area experienced a shift from this particular area to this specific area when I made a slight adjustment to x. Is it satisfactory up to this point in time? What are we supposed to say about this now? Is it okay to express the change in area as delta S since the area has been altered by this much? Is it okay up to here? So you have a F and you increase the area from A to X, and as a result, the area also increased. You mentioned the increase in X as delta X and the increase in area as delta S. Now what can we do with these two rates of change? You can locate the alteration. You are aware of how do I locate the rate of alteration of the region. I intend the rate of alteration of S, taking the change in S as the numerator and dividing it by the change in X, like this. Hey guys, what did I just write? The rate at which S is changing, right? I divided this change by the change, yielding the rate at which S is changing, thereby obtaining the rate of change of S. Is this okay, guys? What's the rate of change for S? Hey guys, here's what we're doing this. You know what I mean? What if we send delta S to 0? What is the outcome that you get when you divide the change by the change and then calculate the rate of change and approach the change in the denominator to 0, which was a technique that we used to employ frequently in the past? So it's about finding the instantaneous rate of change, right? What is this? What is this? Well, it's the rate of change of S, but when you divide delta by delta, it's the average rate of change, so it's the average rate of change. But if I send that change in the denominator, delta, infinitely close to 0, then the instantaneous rate of change comes out, right? Therefore, the manner in which we have collectively decided to represent this symbol is as follows. ds dx. Are you all in agreement with this, gentlemen? I divided the change by the change. If you send the change in the denominator to 0, this becomes dy dx. We've done this a lot while studying calculus, right? This was the process where the slope between 2 points on the graph, y and fx, changes into the tangent line slope, you guys. Right? What are you doing here currently? So I just had this region, and when I increased x, the area changed as well. X and S change simultaneously. To determine the rate of change of the area I was interested in, I divided the area change by the x change. This yielded the average rate of change of S. I represented the area change as ds and the x change as dx. To find the instantaneous rate of change, I set the denominator change to 0. Hey everyone, did all of you follow along well up until this point in time? Take a thorough look. You understand what delta S signifies here, right? It is crucial to grasp the meaning of delta S in this context. Hey guys, this is an area we can't calculate. It's not a polygon, so are we assuming we still don't know about integrals and stuff? So, we are attempting to demonstrate this presently, you know, that we can determine the area enclosed by the curve f from a to b using definite integration. We still do not know that, so for now, we have no knowledge about this area, you guys. But here is the thing, we are considering that there must be a rectangle somewhere in between that has the identical area as this enclosed area by the curve, you know? You understand my point? Once more, you know, there is this strange shape enclosed by this curved object at the present moment. I am curious if there is a rectangular figure located somewhere with an equivalent area, you know? Do you understand what I'm saying by any chance? Is this okay? Where can I locate the rectangle that possesses the exact same area as this particular one in question? When there is a rectangle like this, there will be a moment when the area of this shape and the area of this shape become equal. You know what I mean? So there is a specific point between this one and this one. The way I marked the point is, I just drew a rectangle that has the same area as this enclosed part surrounded by this curve. Do you know what I mean, right? Can you understand the concept I'm trying to explain? I don't know anything about the coordinates of this point, you know, right? I'll call the coordinates of this point C, so I'll just call it C because I don't know what CF means. Just see it like that. Why did we change the area of the rectangle? It's because we can calculate the area of a rectangle by multiplying base and height, right? So, this delta S is the one at present. I transformed this into the area of this rectangle. By the way, what is the area of this rectangle for reference? You know, it's the base times the height. The base is delta x and the height is FC. So it's okay to write it as delta x times FC. Is this acceptable? Why did you make an effort to change her in this manner? Delta multiplied by FC in this way, like this, as you did, as you attempted. So I have this function named fx, and when I started from point A and increased the value of x, the area also increased in size and magnitude. I don't know why you're asking, but I tried to calculate the rate of change of the area. You can calculate the rate of change of area by dividing the change in S by the change in x. I tried to calculate the rate of change, and I just tried to calculate the instantaneous rate of change by sending the change in the denominator to 0. In the process, delta S, which is the area enclosed by some kind of curve, is equal to the area of a rectangle somewhere. I used this fact to determine the x-coordinate, which I just called C. By the way, C is somewhere between these points. In this case, the y-coordinate becomes f of C. So I converted delta S into the area of this rectangle and used it. And that's how I got this result. Now, I modified the denominator in this manner, and then, hey guys, does the change in x simplify or become more manageable? So only the function f is left. Well, let us observe. What is the behavior of the function f as the limit of delta x approaches 0? Examine the picture and provide an answer, guys. Where does the variable f go as the change in x, represented by delta x, approaches 0? Check it out, you all. Look at how this CO is randomly stuck in here. But as delta x approaches 0, it narrows down, right? So when delta x approaches 0 in this picture, it means that this point is moving towards this direction, you know? If delta x is, for example, 1, then the point is here. And if delta x is, for example, 0.5, it would be around this much. The situation where delta x approaches 0 means this point is getting closer. So when we made the assumption of C earlier, we assumed that it was positioned between x, right guys? Therefore, C is gradually getting closer to x as we continue. C is sandwiched between here and here, but when delta x approaches 0, it gradually narrows down. So, as a result, C, which was between here and here, also becomes closer to x. That's what I think. When the limit of delta x approaches 0, I thought of it as the area of a rectangle. It becomes delta x times f of c when I simplify it by dividing delta x. Hey guys, this becomes f of x, right? I tried explaining it with a picture, you know. So dx means the current interval, but dx approaches 0? So this point will gradually get closer to this side, huh? Anyway, this is between these 2 points. You know what I mean, guys? When I write this, I won't write it like this. I'll write it like this because this is delta x. So I'll just write the chords as x plus delta x. It looks better, don't you think? So if delta x goes to 0, does that mean this point gradually moves in this direction? So in between here, something that was in the way, c, will eventually get closer to x, right? You know, in calculus, they call this the sandwich theorem. But since we've never learned such a thing, we call it a squeeze space and a jamming arrangement. When something between them reaches the same extreme value, he also becomes him. There's something like this, but since we haven't learned it yet, I just explained it based on my intuition. This is the result it becomes. Let me try connecting these two things once. Hey guys, what is this? The result of differentiating s with respect to x is fx. So, in the end, when we connect everything, guys, you know we can replace ds with this. What does s mean here? You're talking about integrating this ft from a to x, right? So, like, how are we going to use this kid again? We're going to use him like this. So, you are aware that ds dx represents the integral of f with respect to t from a to x. Hey everyone, I recently wrote this as an integral. It represents the integral of function f from point a to x, measured in feet. You're saying that you differentiated him with respect to x, the derivative of this with respect to x. This is the first step of the fundamental theorem of calculus, where this and this are the same. In other words, if you differentiate f with respect to x from a to x, it becomes f. So, guys, pay attention to where x is. X is right here. And when you differentiate with respect to x, when the variable is here, it becomes f. I will demonstrate it. Allow me to present you with a problem immediately. Listen attentively, gentlemen. If we have an expression like the integral of t squared plus t dt from 3 to x, there exists a method to find its derivative with respect to x. So, gentlemen, what occurs if we differentiate it with respect to x? When x is here, if I differentiate this equation with respect to x, then it becomes fx. They say that if I just substitute x here, it becomes x squared plus x. That's how you write it. So if you want to directly utilize this equation, what is this equation right now? So this is some kind of definite integral with respect to x, guys. Because x is involved, what do you think this function is? So is that x in the interval for the function about x? If you differentiate this with respect to x and substitute x, the important thing is to understand this equation. Let me explain this equation again, guys. First, there is a function called ft, and I simply wrote the area from a to x as LHS. So, I modified x, and it turns out the area also changed. I desire to determine the rate of change, and now two aspects have undergone modifications. Shall we compute the rate of change? I'm curious about the rate of change of s, so I'll divide delta s by delta x. So, if we do this, it's the average rate of change. But since we learned differentiation, if we send the change in the denominator to 0, we know that the instantaneous rate of change comes out, and we agreed to write that symbol as ds, dx. First of all, we've done it up to there. So guys, we can use this area as a symbol for integration. We just wrote that. This is x. Sorry guys, this is dx, right? Did you just write s as the integral from a to x in this equation? Is that all you did? The second step was a bit difficult. What is the second step? I've thought about this again. When thinking about delta s here, delta s means this area Guys, we've changed this area into the area of a rectangle. This thought, there has to be a rectangle located somewhere that possesses an equivalent area as this one. Am I correct in assuming this? So now we're calling that point C, and we change delta S into the area of a rectangle. Delta X times F is called C, and then I realized it simplifies. Is there any carbon left in Fahrenheit? What are we watching? What happens to carbon in Fahrenheit when delta X goes to 0? So when I think about it, saying that delta X goes to 0 means that this point gets infinitely closer to this side. And if this point gets infinitely closer to this side, then the C in between here will also move towards X. So I thought that C in F will change to X in F. Ultimately, this and this are the same. And so when I examine the ultimate shape, if X is present and I take its derivative with respect to X, it transforms into F. This is what we refer to as the initial stage of the fundamental theorem of calculus, or you can alternatively label it as the first theorem of calculus. Is it satisfactory up to this point, gentlemen? Hey guys, we're almost done with the second one. Once we finish number one, we're pretty much done. Take a look. We figured this out. You know what we found? We just proved this, right? Now you all must think carefully, kids. Examine this dish again. Hey everyone, I'll handle it. I will take care of this, just like I always do. Please continue, don't hesitate. Keep going, don't stop. Well, what is it? So, you're asking if the derivative of this square is fx. What did we agree to call our square when that happens? This is the antiderivative, you know. If you differentiate something and it becomes fx, then this square thing can be called the antiderivative of fx, you know. Is this okay? If you differentiate x cubed, it becomes 3x squared, you guys. So if we differentiate x cubed here and get 3x squared, the integral, the antiderivative of 3x squared, is called x cubed, right? Is that correct? That is precisely what it appears to be at this very moment. There is indeed something, and if you differentiate this particular thing with respect to x and it transforms into fx, then this something is, in fact, the antiderivative of fx. Do all of you comprehend and grasp the concept explained in this specific part? If something differentiated as x is fx, then that something is the antiderivative of fx. Hey guys, we usually call the antiderivative of fx as fx, you know? So I'll write it as fx. If this is the case, when we express the antiderivative of f as a function, it would be like this. From a to x, f is the antiderivative of f, so we write it as f and add the constant of integration. Then, shall we substitute x and a into both sides of the equation in order to evaluate the definite integral and determine the value of the antiderivative at x? When I substituted a, I knew that the area from a to a was 0, and I could find the value of c, you know? So, looking at this equation again, since this is the antiderivative of f, we can write it like this. And then, when we substitute x with a on both sides here, it changes to a. And this value is initially 0, and c becomes fa. So we substitute this obtained constant of integration back into c and integrate from a to x for f. So gentlemen, after performing the operation of subtracting f from f, if we ultimately replace x with b, the fundamental theorem of calculus that we are familiar with is derived. Since we have stated that stdt, fx, and dx are all equivalent when we substitute b, if we reverse the substitution of t back to x once more, at the conclusion, the fundamental theorem of calculus that we are familiar with is derived. Hey everyone, how are you all doing? The fundamental theorem of calculus, part 1, is about definite integrals. The fundamental theorem of calculus part 2 is not proven perfectly. I explained something based on my feeling in the middle. For example, earlier like this. There must be a rectangle somewhere with the same area as the enclosed area by this curve. I briefly explained that part with a certain feeling. That part needs to be proven by the mean value theorem. There is actually a theorem called the mean value theorem. You have to write that theorem accurately. And secondly, you have to explain the process of how this changes into that using the squeeze theorem accurately. I skipped that part. Without learning the mean value theorem and the fundamental theorem of calculus, I explained that part based on intuition. Besides, this is the most important theorem in calculus that needs to be proven in the basic theorem of calculus.